We are often promised a version of autonomous development where agents assemble themselves into complex structures, building entire applications while the engineering team sleeps. But the data from 2025 reveals a different reality. 95% of these generative AI pilots fail when they leave the lab. In production environments, long-running agents almost inevitably degrade and crash. These failures are frequently caused by a process mirrored in classic computer science, the malloc-free memory leak. This diagram illustrates context rot. As an LLM processes its own massive conversation history, its working memory becomes so crowded with previous thoughts and logs that its reasoning abilities begin to fracture. Expanding the context window to millions of tokens doesn't solve this problem. It simply provides more room for the rot to grow before the system reaches its inevitable breaking point. Early agents fail by acting as both processor and database. Logic and memory are trapped in the same loop. Storing project state within this active loop entangles history and processing, creating a web that obscures the task. That entanglement is what triggers hallucinations. The agent loses its place in the project, eventually forgetting what it was actually trying to build. Resolving this requires a strict engineering boundary: the total separation of state, the project memory, from logic, the active processing. The diagram now reflects a stable architecture. Computational progress must be saved exclusively in external files, leaving the LLM's internal brain clear for the next task. By stripping the agent of its internal long-term memory, we can prevent the slow buildup of errors that leads to a total system breakdown. This architectural shift is implemented through a specific workflow known as the Ralph-Wiggum loop. The Ralph loop replaces the complex conversational thread with a simple, deterministically naive bash loop. This windshield wiper effect forces a hard memory wipe, spawning a fresh agent on every iteration. Waking up, this amnesiac agent reads only the original, immutable goal specification. Next, it scans the physical codebase to see what previous agents built and where they left off. The agent executes one single action, writes its progress to the files, and is immediately terminated before its context can accumulate any bloat. This makes the execution engine entirely stateless. What was once a destructive infinite loop becomes a series of stable, predictable steps. However, this amnesia creates a tracking problem. If every agent forgets everything every few seconds, a human engineer can't easily see how the system arrived at a specific decision. Traditional text logs are mostly useless here. Trying to read through thousands of lines of flat text to debug a rapidly respawning AI network is a manual nightmare. To manage this, we must move from a black box to a glass box. Platforms like Arise Phoenix map agent graphs, showing the exact decision tree. This framework tracks operational data natively, allowing us to monitor the precise processing time for every branch. Without this graph-based observability, maintaining a stateless agent system is just guesswork. By combining the persistence of the Ralph loop with the deep tracing of an observability platform, we create a system that can build and verify software without manual intervention. This dual-layered architecture allows engineers to catch edge cases deterministically. We can see exactly where a logic branch fails and fix the underlying prompt or tool. This setup provides the stability necessary for agents to build and test entire features without the risk of a runaway memory leak or a $47,000 billing error. Reliable AI deployment in an enterprise environment is less about the intelligence of the base model and more about the rigor of the system's architecture surrounding it.